Jai Hind, welcome to the course Network Analysis and Synthesis, and we are discussing the network synthesis of this course. So, in the last lecture we discussed the synthesis of two elements type one port network. And in this connection we discussed LC network in Foster's form and core forms. Okay, and we have also seen that in the Foster form we carry out the partial fraction expansion, and in the core form we carry out the continued fraction expansion. For the Foster core first we carry out continued fraction expansion about pole at infinity, and for core second we carry out continued fraction expansion about pole at origin. Today we are going to discuss RL networks in Foster forms, means Foster first and second, and core forms and core forms first and second. Okay. So, before going for the synthesis of the network, we will discuss the properties for a RL network, and if time permits we will discuss the RC network. Okay. So, first we will discuss the properties of RL network or RC network. These properties are very helpful in finding out the given network function, whether the RL, RC or LC. So, what are the properties? So, in RL, the property of RL impedance, look at here, and RC admittance is same. So, RL impedance and RC admittance properties are same. So, what are the properties? First is all poles and zeros are simple and located on negative real axis. So, what does it mean? It means this is your S plane, right, and this is your real S and this is your imaginary S, say the j omega axis. So, in this case all the poles and zeros lie on the negative real axis. So, this is minus sigma. So, all the poles lie on this line. Okay. Poles and zeros alternate on negative real axis, understood. The third point is very important, the singularity nearest to or at origin is a 0. It means at the origin there is a 0, then we have the pole, then 0, then pole and so on. So, the singularity nearest to or at the origin is a 0 and singularity nearest to or at infinity is a pole. So, third and fourth points clear. Now, the fifth is residuals of poles of ZRL are real and negative. So, if you carry out the partial fraction expansion and you find the poles residuals, that is the constant K1, K2, K3, they must be real and negative. So, what we will do if you get the coefficients real and negative, what we will do? We go for this, divide the given function ZRL by S and then carry out the partial fraction expansion. It means the coefficient of ZRL divided by S are real and positive. So this is the how we carry out the partial fraction expansion, because here we are getting real and negative. So we cannot stop here. So what we do, just divide the polynomials or equations by s and then carry out the partial fraction expansion. The sixth point is slope of ZRL is positive, or you can say the YRC is positive. And the seventh is ZRL at s is equal to infinity is greater than ZRL at s is equal to 0. If these all 7 properties are satisfied, then the given function is either RL impedance or RC impedance. Suppose a function is given and you are required to find the Foster forms. Okay. So we have decided the given function is RL impedance. So for the RL impedance, you can draw the Foster first, and we also know that the Foster second we go for the admittance. So Foster second we can have the RC admittance. Okay. Now if we are going for the Foster forms, okay, if the function is impedance, remember yesterday we discussed about the LC network. If the function is impedance, we go for the Foster first, and if the function is admittance, we go for the Foster second, okay. And what are the techniques? Technique is same. We go for the partial fraction expansion. So if the given function is ZRL, what we do? Divide by s and then carry out the partial fraction expansion, and we get this form. So what are these constants? This is the removal of a constant. This is removal of a constant. It means if the degree of the numerator and denominator polynomials are same, so to carry out the partial fraction expansion, the function must be rational. So to make the function rational, what we do? We just divide the numerator polynomial by denominator polynomial, and we get this k infinity, which is removal of constant. And this is the, if this is the impedance, okay, so carry out the partial fraction expansion, and after finding this k0, k1, k2, ki, k infinity, we just multiply. So ultimately we get this. So we get this one. Get one. So here this is your removal of pole at infinity. And what is this? This is now removal of constant. This is for ZRL. For ZRL, removal of constant. And this terms k1 as s plus sigma 1, k2 s upon. So these are the factors. How many poles lie on the negative real axis? So we get these terms. So this is basically how many poles are lie on the negative real axis. So we get this. So this is the general expression for the Foster first if the function is impedance. Okay. Now how will we get? So we know that if you are going for the Foster first, so general representation of Foster first is like this. So this is your Foster first, this is your, say if this is impedance, so this is R, this is your L1, this is your C1, this is your L2, this is your C2. So these components we get how many poles lie on the negative real axis, and this is the removal of pole at infinity. So we can get easily this and this we can identify. Okay, we know that Z, if the inductive impedance is SL, so this is the value is, this is the inductor value we can get. The problem lies with L1 and C1. L1 and this is R1. Sorry, this is R1. This is your R2. Sorry. So look at here. This is the parallel combination of resistor and inductor. So convert it into S domain. Find the equivalent impedance. This, okay. This, and finally we get this. So here ZRL S is equal to SR upon S plus R by L, and we have one factor in the partial fraction expansion. We have this factor. If we look at the previous equations, we have this S K1 S plus sigma 1. Okay. Now comparing these two, we can have R1, say this is R1 is K1, suppose this is your R1, so R1 is K1, and R1 by L1, and R1 by L1 is sigma 1. So from this two we can get the value of R1 and L1. So we can fabricate this network, RL network, if the function is impedance and we are going for the Foster first. Similarly, if you are going for the Foster second, so Foster second, the general representation of Foster second is like this. This is the parallel combination of series network. This is your, this is the Foster second. Okay, so this is the general representation of Foster second. So we can see, we can get this easily from the comparison of the partial equation of the partial fraction expansion. The problem lies here. How will get this R1 and L1 in case of Foster second? So look at here. Suppose I have drawn here R1 S1. So same approach we can have. In the place of capacitor we can have the inductor. So this is, suppose we can have, this is your R, this is your SL. Okay, so ZS is R plus SL. Okay, and YS, so YS is 1 by R plus SL. So take L outside, so it is R plus S plus R by L. So if you are going for the Foster second of the RL function, then you have to compare with this, with the partial fraction expansion, and we can get this value. So what is, so this is basically, this is 1 by L, we can get the with the multiplied with the coefficients, and this is the R by L is equal to sigma 1. So this way we can get the value of this R1 L1, R2 L2, and R3 L3, and so on. Now come to the problems. The problems is like this. Synthesize the given network in Foster forms which are given by this. It is in the form of the network function. The first and foremost, you have to identify whether given Fs is RL or RC. RL impedance or RC admittance, the property is same. Okay. Once we find the Fs is either RL impedance or RC impedance, then we can proceed. So first look at this function. So draw here, just draw here the S plane. This is your sigma, this is your j omega. So singularity nearest to origin is a 0. So 0 is here, minus 1, this is your 0, because zeros are, if we equate zeros are at S is equal to minus 1 and minus 3, and poles at s is equal to -2, -4. So the singularity nearest to origin is a 0, then we have the pole, then 0, then pole. So first, second and fourth property. For first property is poles and zeros are simple and lie on the negative real axis, that is true. First property is true. Second property is poles and zeros alternate on the negative real axis, this is also true. The singularity nearest to or at the origin is a 0, that is also true, and the singularity nearest to or at the infinity is a pole, this is also true. Now if you carry out the partial fraction expansion, the poles and the residuals are real and negative. So the and find once more f infinity and f 0. So put s is equal to 0. So put s is equal to 0, how? S is equal to 0 is equal to 3 by 8, and f infinity we can take the s outside. So 1 plus 1 by s, then 3 we can take the s, so s of 1 plus 3 plus 1 by s, and so on. So we can see that the f infinity is greater than f 0. So this all four properties satisfying, it means the given fs is ZRL or YRC. So we have find that this given function fs is ZRL or YRC. Now the question is Foster forms. So this problem can be solved in the three different ways. Some will try to find the once ZRL Foster first, YRL Foster second. Some people will do like this. The second set of people will do? They will do ZRL of Foster first and YRC Foster second, because it is not written whether we have to find the RL network or RC network. So one may go ZRL for Foster and YRC Foster second, because we know that for the Foster second the function must be admittance. The third set of people, what will they do? They go for ZRL for Foster, ZRC for the Foster first, and YRC Foster second. So one combination is Foster first of RL impedance, Foster second of RC admittance, one set. Second set is Foster first of RL impedance and Foster second of RL admittance, and third set will be Foster first of RC impedance and Foster second of RC admittance. So if you not written whether we are going for the RL impedance or RC impedance, so this problem can be solved in three different ways, and all three figures are correct. So once we have decided the given function is ZRL, so carry out the partial fraction expansion. So what we do, because we know that this is real and negative, residuals are real and negative, residuals are real and negative. So divide by s. So this is the way to carry out the partial fraction expansion. So divide the function by s. Now carry out the partial fraction expansion. So we have this one, then this. So three terms. Now then find the k0, k1 and k2. So we can get k0 is 3. How will get is very simple. So ZRL upon S is equal to K0 by S. Okay, K0 by S, K1 S plus 2, K2 S plus 4. So K0 is S into S plus 1, S plus 3, okay, S into S plus 2, S plus 4, S is equal to 0. So this cancel out, so 0, 0, this is 0, this is 0, 3 by 8. So and this way we can find the K1, K2. So these are the poles residual, 3, 1 by 4, 3 by 8. Now then find the ZRL S. So this is 3 by 8, okay, this is 1 by 4 into S divided by S plus 2, and this is 3 by 8 S divided by S plus 4. So there are 3 terms. So this is a impedance, this is impedance, so this is also impedance. What is which type of? So this is resistive, and by comparing with this, we have in the previous slides we have just find the value of R1 and L1. So from here we can get the R0, we can get the R1 L1 and R2 L2. So this is constant, this is R1 L1, this is R2 L2, and how will get it? Compare with this. So 1 by 4, R1 is 1 by 4, so and L1 we can get 1 by 8, R2, and this one comparing. So what you have to do, just take the impedance of this and compare with this, okay. In the previous slides we just explained, take the equivalent impedance of this and compare with this, we can get the R1, R2, L2, and so on. So this way we can solve the problems. So this is the first or second, same, this is the partial fraction expansion, this is the RC network, find the equivalent admittance of this, compare with this, we can get the value of R1 C1, R2 C2. So this is the first or second of YRC. First or second of RL. So this is the given function. So this is the YS. Carry out the partial fraction expansion. Before carrying out, just this is the degrees is same. So divide the numerator polynomial by denominator to make the function proportional, and then carry out the partial fraction expansion, and you can get the value of K1, K2, and this way we can get the. So this is the Foster's second of RL, and we can similarly we can have the Foster first of the RC. So this numericals or these problems can be solved in 3 different ways if nothing is mentioned. Suppose the question is asked, find the RL Foster forms. So you have to go for the RL network, it is impedance, then invert the function to make the admittance and carry out the partial fraction expansion. So chord first and chord second, these forms of RL network we will discuss in the next class. Procedure is same. First find the poles at infinity and carry out the continued fraction expansion. To carry out the continued fraction expansion, going for the chord first, arrange the polynomials in the descending order and divide the numerator polynomial by the denominator. For the chord second, that is the removal of pole at origin. So what we do, we just arrange the polynomial in ascending order and then divide the numerator polynomial by denominator, you can get the chord first and chord first. Procedure is same as we discussed in the LC network, same procedure is applied for the RL network. So in the next class we will discuss the chord forms and the Foster forms of RC network. So thank you very much. Jai Hind.